All right, so when it comes to antiderivatives, there's some various notation we use. We'll probably move pretty quickly to the integral notation. But for now, you might say something like, well, if f of x is equal to x squared, we might use capital F for the antiderivative. That's a pretty common thing to do before we use the antiderivative integral notation. So the antiderivative is 1/3 x cubed plus any constant you like. Plus 2, plus pi, plus e, plus the square root of 7. We don't want to write all those, so we're just going to write plus c. The reason this is true, and this is kind of the most important part of this, is that this function, 1/3 x cubed plus c, is the antiderivative of x squared because the derivative of that function there is the derivative of 1/3 x cubed plus c, which is 1/3 times 3x squared plus 0, which is exactly x squared. That's the whole story. I mean, there's a lot of pieces to this story, but that's the big picture. The reason antiderivatives are what they are is because if you take the derivative of the antiderivative, you end up back at the function you started with. In fact, let's write that down. The derivative of the antiderivative, I don't know if there's a hyphen there or not, I don't care, of a function f of x is, drumroll please, f of x. You find the antiderivative, and take its derivative, back where you started. This is essentially the gist of the first part of the fundamental theorem of calculus, which we will get to eventually. Also, if this is in anyone's way, you're welcome to sit in a different seat if that's better. I don't mind. Questions about that statement there? All right, let's do a few more examples. So this idea here is generally referred to as the anti-power rule. I'm always worried like I'm going to bump something out and make it all not work. So in general, or at least I call it the anti-power rule. You might call it something else. The anti-power rule, sounds like we're fighting the power, is that if your function is x to some power, then the antiderivative, which again, we're going to use this capital letter to represent the antiderivative for now. The antiderivative is x to that power plus 1 divided by that same power plus 1 plus c. So for example, I'm just going to start using this notation because it gets to be a real pain in the butt to keep writing the antiderivative of this function is this function. We'll come back around later to talk about why this integral notation is the correct notation to use for antiderivatives, because it's a very, very logical is not the right word. There's a very deep connection between integrals and antiderivatives. They're not exactly the same thing, but they might as well be. So the antiderivative of x to the 6th power, so this elongated s means antiderivative of this dx here, that is a d, means the variable x is the variable that we are antidifferentiating. The antiderivative of x to a power is x to that power plus 1 divided by the new power plus 1 plus c. And you can write it as x to the 7th divided by 7, or you can write it as 1/7 times x to the 7th. Either way is fine. Sometimes it's more convenient to write it like this. Sometimes it's more convenient to write it like that. There is a power this won't work for. What could P be here that would be problematic? Almost. Almost. One more. -1. So this doesn't work if P is equal to -1. Because if P is equal to -1, you're going to get division by 0. We'll come back around to that in a few minutes here. So we can kind of apply some general ideas here and say, if I want to say, I'm going to go back and forth between this integral notation and not, just because I think it's good to talk about all the notation. If g prime of x, the derivative of g, is equal to, sure, what do I got here? X to the 8th plus the cube root of x minus 1 over x to the 5th plus 6. I want to find the antiderivative, which I'm going to call g of x, because the antiderivative of the derivative is just the function. So we're going to find g of x. Before I do that, it is in my interest, it's in your interest to simplify this expression as much as possible. Specifically, I want to rewrite all these things as x to a power. Not 1 over x to a power, but x to a power. So I'm going to read, well, x to the 8th is fine. So g prime of x, I'm not finding g of x just yet. I'm just simplifying the thing they gave me is x to the 8th plus x to the 1/3 minus x to the -5th plus 6. And now we're going to anti-differentiate term by term. And much like differentiation, when you differentiate a bunch of things added together, you just take the derivative of each thing and add the results together. The same idea applies to anti-differentiation. We're going to anti-differentiate all these pieces, and then we're going to add or subtract the results together. Pretty straightforward. So g of x, the antiderivative of the derivative of g of x, is x to the 9th over 9, plus, let's not add fractions just yet. Let's do x to the 1/3 plus 1 over 1/3 plus 1. Totally fine to write that and then simplify it later. We're going to get minus x to the -5th plus 1 divided by -5 plus 1. And finally, I mean, not quite finally here, what's the antiderivative of 6? Right. Another way you should ask that question, you really should ask the question yourself, like the words I'm actually saying in my head when I say what's the antiderivative of 6 is, what function has a derivative equal to 6? Oh, 6 times x. Because we know the derivative of a constant times x is just the constant. So whenever you're anti-differentiating a constant, you get that constant times x. And then, of course, plus c. We should simplify this. It's almost always good to simplify these things. I should say one exception might be if you're doing homework in web work and the simplification is terrible, web work will totally take your unsimplified answers and simplify them for you, or at least give you the final expression. So you could enter this into web work and it would be correct, even though it's right. Why are you going to write -5 plus 1? You should write negative. So definitely do the simplification along the way that makes sense to do in web work specifically, and then don't do the ones that don't. I wrote this as 1/9 x to the 9th just because 1/3 plus 1 is, oh, not equals, James. Holy smokes, there's a plus sign there. X to the 4/3 dividing by 4/3 is the same as multiplying by the reciprocal 3/4. And we often kind of just do that automatically. -5 plus 1 is -4. And then we're dividing by -4. So let's say a minus is plus 1/4 x to the -4th plus 6x plus c. And there is our antiderivative. Questions? It's not my best habit to ask for questions like that, but I'm going to do it often. I'll try not to. You should just ask questions if you have questions. Stop me if you have questions. Say, hey, James, I have a question about that, or I wrote something terrible. I will do my absolute best not to be like, hey, you have any questions? But we all have our own foibles and patterns. Yeah, sure. What if, come on. What about the antiderivative of something like 6x squared? Ooh. What's that 6 going to do? Well, I like to say it hangs out. It's a constant multiple. And again, a lot of the derivative rules that we've talked about in 17A or whatever your previous quarter of calculus was, a lot of those derivative rules have analogous antiderivative rules, like adding or subtracting functions or multiplying functions by constants. So when you take the derivative of a constant times a function, like the derivative of 5 times x to the 7th, we don't even think about using the rule. We just know it's 35 times x to the 4th. But really the rule you're using there is the fact that the 5 hangs out. The derivative of x to the 7th is 7 times x to the, I said 4th, sorry, 6th, apologies. Correct me if you hear me saying something stupid. Or let me know, I suppose. And then 5 times 7 is 35. We do that kind of automatically, but really the rule we're using there is that the derivative of a constant times a function is the constant times the derivative of the function. That works for antiderivatives as well. the antiderivative of 6 times a function is going to be 6 times the antiderivative of that function. And then we can anti-differentiate and get 6 times x squared, x cubed over 3. And then 6 over 3 simplifies to 2. So we get 2x cubed. Let's see. We would probably skip all that work generally and be like, oh yeah, I know I'm going to add 1 to the power and get 3. And when I divide by 3, 6 over 3 is going to be 2. But this is the work that's happening there. Constant multiples hang out is what I often say. And that's true no matter what kind of function you're dealing with, whether it's a nice power of x or a polynomial or a trig function or any other kind of thing. So for example, if you're integrating something like 5 times cosine of x, the 5 would hang out. And the antiderivative of cosine is so close. Negative sign was closer. Positive sign. So the derivative of cosine is negative sign. The antiderivative of cosine is positive sign. Because what's the derivative of sine? Positive cosine. So yeah, there's kind of a nice thing I've seen people do before is if you like, you can write like, I don't know, sure. Y equals sine of x, and then just start listing the derivatives. The first derivative is cosine of x. The next derivative is negative sine of x. The next derivative is negative cosine of x. And the next derivative is positive sine of x. So if you read down the table or list or whatever you want to call it, you're taking the derivative. But if you read up the list, you're taking the antiderivative. Or an easier way maybe to remember it, for sine and cosine specifically, the derivative and the antiderivative are always the opposite SIGN sign. It's really unfortunate that the sine function sounds like the same as the word SIGN, but such is life. So derivative of sine is cosine, antiderivative of sine is negative cosine. Derivative of cosine is negative sine, antiderivative of cosine is positive sine. Not too terrible. Other functions don't work that way, but sine and cosine are kind of special. So it's good to remember that if you know the derivative of sine and cosine, you know the antiderivative, just change the positive or negative to the opposite of what it would have been. Okay. What else do we have here to look at? Oh, sure, lots of other fun things. Let's look at that. So really, any function you know how to take the derivative of, that result, you know how to take the antiderivative of. For example, if I was going to find, say, the antiderivative of 3 over 5x squared plus 8 over the square root of x plus secant squared of x, with a little simplification / rewriting, these all look like things that we recognize as derivatives of other things. I'm going to rewrite this just like I did for the previous one. I'm going to write any powers as not in the denominator because that's not helpful to me. I'm going to rewrite this as the antiderivative of 3 over 5 times x to the negative second plus 8 times x to the negative 1/2 plus secant squared of x. These first two things, we just use the anti-power rule. So we get 3/5 x to the negative 2 plus 1 is negative 1 divided by negative 1. This one's a little dicier. We get 8 times x to the negative 1/2 plus 1 is positive 1/2 divided by positive 1/2. And finally, who has a derivative that's equal to secant squared of x? Tangent, good old tangent. Tangent of x. Let's see. And then we would simplify. I would rewrite this as negative 3/5 x to the negative first. 8 divided by 1/2 is 8 multiplied by 2. So 16 times x to the 1/2 plus tangent of x plus c. It would also be perfectly reasonable to write this as negative 3 over 5x. And this is 16 times the square root of x. Either way, doesn't really matter. I will say, I know I just said it doesn't really matter. It kind of matters sometimes. Here's why it matters. If I had to take another antiderivative of this for whatever reason, I would want to leave it like this because having things as powers is nice because I know how to anti-power rule things. The negative one, yeah, okay, it's a story we're going to get to in a second. On the other hand, if someone had asked me about the domain of this function for some reason, I might prefer to write it like this because writing it this way, it's more obvious to me that 0 isn't in the domain because I can't divide by 0, and that x can't be negative because I have a square root of x. Writing it as x to the negative 1 and x to the 1/2, to me, hides that fact a little bit. So depending on what I'm being asked to think about, it might be good to be able to go back and forth between these two different ways of writing things. I'm just going to keep throwing examples at you. Why don't you all try this one? Or actually, sure, yeah. The integral, the antiderivative of x to the 4th times x cubed plus 3x dx. And I will point out, we do not have what you would think of as an antiderivative product rule. So before you can antidifferentiate this, what do you need to do? Simplify it, for lack of a better word, or distribute the x to the 4th if you want to be more explicit about what we're doing here. So go ahead and do it. Distribute the x to the 4th, antidifferentiate those terms, see what you get. You'd be like 45 seconds. If we simplify this, it's equal to the antiderivative of x to the 4th times x to the 3rd, which is x to the 7th, x to the 4th times 3x, I should say plus x to the 4th times 3x, which is 3x to the 5th. Then we use the anti-power rule. We get x to the 8th divided by 8 plus 3x to the 6th divided by 6 plus c. We should simplify that as x to the 6th over 2. There's our simple antiderivative. So again, any function that you know how to differentiate, you know how to antidifferentiate the result. So all the trig functions we talked about on Wednesday, all those derivatives we know how to antidifferentiate. So we already talked about sine and cosine and secant squared, but we also know that, say, if the derivative of secant of x is equal to secant of x times tangent of x, then for sure we can say that the antiderivative of secant of x times tangent of x is equal to secant of x plus c. That's the whole relationship. I know I'm going to say it like a bunch of times. It might sound kind of annoying after a while, but it's really, really, really important that you understand that the process of doing a derivative and an antiderivative essentially undo each other. Technically, if you do a derivative first and then an antiderivative, you don't get back to exactly where you started because there's this plus c at the end. But okay, it's essentially the same. The other couple trig functions that we hadn't addressed yet, we know that the derivative of cotangent of x is negative cosecant squared of x, which means that we can say that the antiderivative of cosecant squared of x dx is negative cotangent of x plus c. It's more typical, like you wouldn't usually write the integral of negative cosecant squared is positive cotangent. We usually bring the negative over to the other side of that just to make it look nicer. In a similar way, we know that the derivative of cosecant of x is equal to negative cosecant of x times cotangent of x. So we also know that the antiderivative of cosecant of x times cotangent of x is equal to negative cosecant of x Let's see. What other functions have we talked about yet? Talked about trig, talked about polynomials. There's other functions. Like, we know the antiderivative of e to the x is itself. And to finish off all the powers of x, we know that the derivative of the natural log of x is equal to 1 over x, which is x to the negative first. Last class, I did mention how the derivative of the natural log of the absolute value of x is also equal to 1 over x, which is x to the negative first. This one here is for x being positive, because you can't take the natural log of a negative number or 0. But here, this one is for all x that are not 0. So this is what we prefer when we start talking about anti-differentiation, because you can say the antiderivative of 1 over x is equal to the natural log of the absolute value of x plus c. Because exactly the derivative of that is equal to that. So the antiderivative of that is equal to that. Back and forth all the time, every time, always, always, always. It is vital that you do write the absolute values there. You have to write the integral or the antiderivative of 1 over x is the natural log of the absolute value of x. Occasionally, you will see it not written in the solution for reasons that might not be made immediately clear. But let me point out an example of that. Yeah, why not? Sure. So let's do the following. Let's take the derivative of the natural log of x squared plus 1. In fact, you all take the derivative of the natural log of x squared plus 1. You got 25 seconds and 35. Right. The derivative of the natural log of x is 1 over x. So the derivative of the natural log of some stuff is 1 over the stuff multiplied by the derivative of the stuff, which is 2x, which you would probably prefer to write as 2x over x squared plus 1. So then we could say the antiderivative of 2x over x squared plus 1 is equal to the natural log of, it would be correct to write the absolute value of x squared plus 1, but you don't actually need it here. Because x squared plus 1 is already always positive, no matter what you pick for x, right? You square it, it's bigger than or equal to 0. You add 1, it's positive. So in textbooks, often you see an answer like this written without the absolute values because they're just not needed. And they usually don't explain what they're doing. They're just like, oh yeah, they don't even write this. They say the answer is this. Because for all intents and purposes, they are the same. As long as the argument inside the logarithm is already always positive. So just be aware, sometimes you won't see an absolute value in a solution manual because it didn't need to be there. But it's always not, don't say all those negatives. It's always perfectly fine to write the absolute values there if you're integrating 1 over x or something like that, where you get a natural log of the absolute value of the thing. A couple other functions we should be aware of. The antiderivative of 1 over x squared plus 1. Well, let me tell you what it's not. It's not the natural log of x squared plus 1. We just did that one, right? The antiderivative of 2x over x squared plus 1 is the natural log of x squared plus 1. So the antiderivative of 1 over x squared plus 1 can't be the natural log of x squared plus 1. What's a function whose derivative is 1 over x squared plus 1? I might have written it last time as 1 over 1 plus x squared. Yeah, good old arctangent. Arctangent of x plus c. Or if you prefer, inverse tangent of x plus c. Either way of writing it's perfectly correct. I prefer arctangent, but you might prefer inverse tangent. And I guess because we talked about it last time, we have the antiderivative of 1 over the square root of 1 minus x squared. dx, and that is the arc sine of x plus c, or the inverse sine. I don't imagine this will come up because it usually doesn't come up in 17b, but it's good to cover our bases. Yeah, there's something else on my mind. Oh yeah, all that. Okay. Sure. So let's look at something a little trickier. Yeah, let's look at something like this. Let's say we want to find the antiderivative of e to the 3x plus sine of 2x dx. We're not quite at u substitution, I think. But this problem could be done via u substitution if you wanted to, but I don't want you to. I want you to be able to do a problem like this where the choice of the thing, I know I'm talking about a thing we haven't even done yet. The choice of u is simple. When I say simple, what I really mean is a multiple of x, a constant multiple of x. So like the 3x or the 2x here. So this is alluding back to what I said last time. We're going to come back to this in a second. What's the derivative of e to the 3x? Well, it's e to the stuff multiplied by the derivative of the stuff. Well, look, the derivative of this thing is equal to that thing. So I could also say the antiderivative of that thing is equal to that thing. So it's also true that the antiderivative of 3 times e to the 3x is equal to just e to the 3x plus. But constant multiples are kind of very easily manipulated. We can move that 3 that's out in front of the function that we're anti-differentiating kind of however we like. Like you can write it out in front of the antiderivative symbol, and then you could divide both sides by 3 or multiply both sides by 1/3 and say that the antiderivative of e to the 3x dx is equal to 1/3 times e to the 3x plus 1/3 times a constant is still a constant, which I'm just going to call c. I know it's kind of annoying, but people do it all the time, so get used to it. So here's what I want you to see. No pun intended there, but it made me laugh. What I want you to see is that differentiating this function made us multiply by 3. And anti-differentiating the same function made us do what? Divide by 3. The same is true for the sine of 2x. The antiderivative, pardon me, let me slow down there. The derivative of sine of 2x is cosine of 2x times 2. The antiderivative of sine of 2x, well, it's not cosine, it's negative cosine, because, right, negative, but it is negative cosine of 2x divided by 2. Or if you prefer, and I do here, negative 1/2 times cosine of 2x. Because if you took the derivative of that, what do you mean if, James? Let's just take the derivative and see. If we take the derivative of negative 1/2 cosine of 2x plus c, the negative 1/2 hangs out. The derivative of cosine of some stuff is negative sine of that stuff, chain rule, multiplied by the derivative of the inside stuff. And oh, look, the 2's exactly cancel, which is why we needed to divide by the 2 in the first place, so that the eventual multiplication by 2 cancels out. So the negatives cancel, the 1/2 of the 2 cancel, and you get exactly sine of 2x. Sorry, I should have also said the derivative of c is 0. Okay. So look, the derivative of negative 1/2 cosine of 2x plus c is equal to sine of 2x, which means the antiderivative of sine of 2x must be equal to negative 1/2 cosine of 2x plus c. Always. The derivative of one thing is the other thing, then the antiderivative of the other thing is the first thing. I'll probably only say it 200 more times. So this antiderivative is equal to 1/3 e to the 3x. And let's just write a minus 1/2 cosine of 2x plus c. the big picture thing I want you to be taking away from this is that if the derivative would have made you multiply by a constant, usually because of the chain rule, the antiderivative is going to make you divide by that same constant. It only works for constants. So just to make sure we're all being extra super careful here, it does not work if you have something like the antiderivative of e to the x squared. Yes, the derivative of that would be e to the x squared times 2x. The antiderivative, unfortunately, is not e to the x squared divided by 2x. There's a couple ways of checking that. You could actually take the derivative and see. Let's actually do that. Let's take the derivative of e to the x squared divided by 2x, which sounds terrible, by using the quotient rule. Let's see, it's the bottom times the derivative of the top, which is e to the x squared times 2x, minus the top times the derivative of the bottom, which is 2, all over the bottom squared. And I'm pretty sure that's not going to simplify to e to the x squared. Like I could factor out an e to the x squared on top, and I'm still left with a 2x times 2x minus a 2 all over a 4x squared. Yep, not quite there. Actually, not that far off, right? If there wasn't the minus 2 there, it'd be perfect. Even sadder story. The antiderivative of e to the x squared is not a function that we know. Or more specifically, there isn't an antiderivative of e to the x squared. At least not a nice explicit one that you can write like sine of x or cosine of x or whatever. There just isn't. And there are lots and lots of functions actually that have this quality, that they just don't have an antiderivative. Now, if you've ever taken a stats class, you might recognize that the integral of e to the x squared is very related to the area under the bell curve. So even though this function doesn't have a nice antiderivative, people have still spent a lot of time. That's actually e to the negative x squared. Sorry, they're almost the same. People spend a lot of time finding the area under that thing because it's very useful. And there is a function you can define, just is literally the antiderivative is written as the integral of that. It's kind of super annoying. Yeah. So back to the more important thing. Anti-differentiating things where we could be dividing by constants. For example, yeah, you also try the following one. The antiderivative of e to the negative 10x plus cosine of 7x. Do I have one more piece to this? Sure. Plus 2 over x squared plus 1. Anti-differentiate that. It's not too terrible. Also, I will mention I do have to leave right at 2 today. So if you have questions, ask me after class. I don't have time for that today specifically. Normally, I'm happy to hang out after class for a minute or two and answer any questions. But today I need to go over to Wellman right away. So don't ask me questions after class today. Other days, totally fine. Maybe we should do one of those. One of those too. So let's take a look and see what we've got here. So the antiderivative of e to the negative 10x should be e to the negative 10x divided by negative 10. Because this derivative will just make you multiply by negative 10 and the negative 10 will cancel out. The antiderivative of cosine of 7x is going to be sine of 7x divided by 7. And the antiderivative of 2 over x squared plus 1 is going to be the antiderivative of 2 times 1 over x squared plus 1. The 2 hangs out. And the antiderivative of x squared plus 1, as we've seen already, is the arctangent of x. Could you write that more nicely? Maybe. You could, I guess you could write this as negative 1/10 e to the negative 10x, but nobody cares. That's not true. Somebody somewhere probably cares. Yeah, let's look at that. couple other things that are interesting here. Yeah, let's do two of those. Let's look at this one for a second. The antiderivative of 1 over 3x plus 2. So usually when I'm looking at an antiderivative, I'm looking at kind of what function does that look like in my catalog of functions, meaning is it x to a power? Is it a trig function, sine, cosine, tangent, secant, cosecant, cotangent? Is it e to the x? Is it something to the x? Is it 1 over x? Right, those are kind, or not, right, 1 over x because it's related to natural log of x. Those are the kind of things, or is it 1 over x squared plus 1? I feel like that's kind of the whole list, the things I'm looking for. Like, do any of these things pop out as the thing I'm trying to anti-differentiate? To me, this one looks closest to 1 over x, specifically because the denominator is a linear function of x, meaning it's, if you just look at the denominator, 3x plus 2 is the equation of a line. I should say y equals 3x plus 2, but get the gist. So if you have 1 over something that's a linear function of x, it's almost assuredly going to anti-differentiate as the natural log of that stuff. Almost. Let's say the answer, which I know is wrong, is the natural log of the absolute value of 3x plus 2 plus c. Let's check it. So we take the derivative of the natural log of the absolute value of 3x plus 2. When you take the derivative, you can really just ignore the absolute value. I guess I should write the plus c. It's going to be 1 over the stuff. What number do I have to multiply by here? Thank you. Oh, but I didn't have a 3 there, right? My integral, my antiderivative was just the antiderivative of 1 over 3x plus 2, not 3 over 3x plus 2. So what am I going to do? I'm going to divide by 3 or multiply by 1/3. So now the 3's cancel. And the derivative of 1/3 natural log of 3x plus 2 is equal to 1 over 3x plus 2. So the antiderivative of 1 over 3x plus 2 is 1/3 times the natural log of the absolute value of 3x plus 2 plus c. Or if you prefer, although I don't, the natural log of the absolute value of 3x plus 2 divided by 3 plus c. I just feel like that doesn't look as good, but either way is totally correct. So just like the other ones, if the derivative would have made you multiply by a constant, not even going to say the words. I guess I am. The antiderivative is going to make you divide by that constant. So it's really good to think about. If you have something where it looks kind of chain rule-y, like you got a function and another inside part, if the derivative of that inside part is a constant, in other words, if the inside part is a linear function of x, it almost always means you're going to dividing by the coefficient of x. Almost always. Probably always, but it's never good to say always, because then someone comes up with a nice counterexample. You're like, damn it. So, in a similar way, if I was trying to find the antiderivative of 1 over, say, 3 minus 7x, same deal. Same-ish deal. It's going to be the natural log of the absolute value of 3 minus 7x, but then I have to divide by what? I know you know how to say words and numbers. Almost. -7. I like -1/7 out in front. But yes, you can either divide by 7, sorry, -7, or multiply by -1/7. Plus c. The check always is that if you know your differentiation rules well, should, it's kind of the key to success in this part of the class, you can take the derivative of this and see that it ends up actually equaling that perfectly. I think I had another example in my mind that was really kind of pertinent here. Oh yeah, I know what it was. This one's kind of funky. The antiderivative of 6 to the x power. I guess this one's kind of chain rule-y too. It just feels less like it. So here's the thing you want to remember about things raised to the x power. Usually their antiderivative is pretty much the same. The best example is, of course, e to the x. The antiderivative of e to the x is e to the x. The derivative of e to the x is e to the x. For other bases, though, it's a little wonkier. Not a lot, but a little. We know, or at least I mentioned last class, that the derivative of 6 to the x is 6 to the x times the natural log of 6. So hey, look, the derivative of my function, I ended up multiplying by a constant. It's not everyone's favorite constant. Probably not anyone's favorite constant. But natural log of 6 is a constant. I don't know, something. It's like 0.8 something, I don't know. What that means is our antiderivative can be found in the same sort of way I've been talking about. The antiderivative here is going to be 6 to the x divided by the natural log of 6 plus c. This one I feel like we should check. It's a good idea to check it. So just as a reminder, if I take the derivative of a constant times a function, excuse me, that constant times a function just gets to hang out. Constants on their own, the derivative is 0. Constant multiplied by functions, the derivative, well, the constant just hangs out. Right, so just be careful though, right? Because people are always like, why isn't the constant derivative 0? It's because it's multiplied by a variable. And there's a variable right there in the 6 to the x. So the derivative of this constant times this function is that constant times the derivative of 6 to the x, which is 6 to the x times the natural log of 6. And oh, wouldn't you know it? Those constants divide to 1, and you just get 6 to the x. So since the derivative of this 1 over natural log of 6 times 6 to the x plus c is equal to 6 to the x, the antiderivative of 6 to the x has to be 1 over natural log of 6 times 6 to the x plus c. There's no other choice. Oh, it's almost time. All right, let's see. Anything else I want to say here? Oh, yeah, let's do that. There isn't a whole, like, there's a minimal amount of trig in this class, but there is some trig. One of my favorite hard integrals that's not really that hard is the integral of tangent squared theta d theta. Sure, let's use theta instead of x. We often use theta for instead of x when we're doing the trig functions, although you could totally use x as well. Tangent squared. So a lot of the time with trig functions, you're going to need to use appropriate trigonometric identities. And this is probably my favorite trig identity ever, because one time a student told me the following thing, which is unforgettable. They said to me, I tanning it sexy. And you can't forget it. It's immediately in your head forever. I've tried to forget it. It won't go away. But it is true that 1 plus tangent squared equals secant squared x, or sorry, 1 plus tangent squared theta equals secant squared theta, and I get sexy. I don't tan, though. So. Anyway, that means that we can replace the tangent squared with secant squared theta minus 1. And then we can replace the integrand, or the thing we're anti-differentiating, with secant squared theta minus 1. And we know that the antiderivative of secant squared of a variable is tangent of that variable. So we're going to get tangent of theta. What's the antiderivative of 1? That's the derivative of 1. I want the antiderivative of 1. What variable has a derivative that's equal to 1? X, or in this case, theta plus c. It's a very hard question if you don't know how to do it. It's a very easy question if you know the trick. Unfortunately, that's kind of a true statement for a lot of integration, is it's very easy once you've seen the trick or the method. It's very challenging if you don't know the way. The last thing I'll say, we're not really there yet, though, but eventually we'll talk about how to integrate something like this, 2x times cosine of x. What I really want you all to take to heart right now is that the antiderivative of this is not x squared times sine of x. You cannot anti-differentiate a product of two functions by anti-differentiating each part and then multiplying it together. Because if you took the derivative of this, take the derivative of x squared times sine of x, what derivative rule would we have to use? For the product of x squared and yes, exactly. So it'd be 2x times sine of x plus x squared times cosine of x. which is certainly not the same as 2x times cosine of x. So later on, probably in a week or so, we'll talk about how we anti-differentiate things like that using what's called integration by parts. But for now, we're not there yet. But I just want you to be, I really want you to know that you can't integrate something times something by doing the antiderivative of the first thing times the antiderivative of the second thing. It does not. All right, that's it. Have a lovely weekend.